All right. In this particular example of vector addition, this is probably, I would say, the most involved in terms of just finding your answer in component form, is if they actually provide you with magnitude and direction. With the previous two types I've looked at, they either handed me component form for both, which is just a matter of adding them up, or they handed me the points where I could sketch quick diagrams and easily find the component form at a quick glance for the most part. So both of those were pretty steadfast, pretty straightforward. But this one's actually not much more involved. It looks a little messier, I think, when it's all said and done, just because of the nature of the problem. But a reminder to us is that the x component of a vector, if I need it, which I will, because we're working with component form, is the magnitude of that vector times cosine of your direction angle, remembering that we consider our direction angle from the positive x-axis, rotating it in a counterclockwise direction. And that's not always how we'll talk about angles, but for a generic problem like this, that's how we want to look at it. And then here, for a y component, the reminder is to swap that cosine out for a sine instead. Those two little formulas are both going to each be used twice. We'll find our component form for A, we'll find our component form for B. And once we've done that, we're done with the problem. We just got to add those things up. And there'll be a little bit of rounding in this, so our answers may be slightly different than an answer somebody else might get, depending on how they rounded their problem. And I will try to save my rounding until late in the problem. And I'll show you what I mean by that as we get to that point. So I'm just going to set a few things up here. I know that AX is going to be 7 cosine of 139 degrees. So I take the magnitude and I multiply it by cosine of that. And I know that AY is going to be 7 sine of 139 degrees. So very slight change there. The cosine and sine just orient direction. Cosine tends to be associated with x's. Sine tends to be associated with y's. And we're going to set the same thing for BX, which is 6 cosine of 254. So we're just using B's values now. And our y component for that one is going to be 6 sine of 254. So again, this is actually one of those kind of really repetitive situations. And actually, I was originally going to go ahead and just kind of round off values here and just kind of drop them in and then add them up rounded. But we can, if we have the right calculators, do this pretty cleanly and get as accurate of a rounding answer as we can. What I want to do is remember that A plus B, which they're asking for, is AX plus BX, and then AY plus BY. Well, honestly speaking, with the calculator I'm going to be using, this TI-84 Plus, I can just type in 7 cosine 139 plus 6 cosine of 254. I can actually just input that exactly into the calculator. So what I mean by that is I'm going to type this in like this. Because that is AX plus BX. And I'm actually probably not going to have enough space here. I'll try to write this down. Maybe I'll write just a little smaller here. Oh dear. That hole in the page really got me there. So this vector can easily be found to the most accurate degree here by just kind of plugging it like this. So let's take a look. We have 7 cosine of 139. We have 6 cosine of 254. And we're just going to add those up. And I'm going to take a look at that and go, first of all, maybe that number feels weird. We don't know. Our original problem didn't have any negative values in it. But our angles were all rather unique. So 139 is an angle in the second quadrant. 254 is an angle in the third quadrant. I actually am expecting to see some negative values here. But if I wasn't sure, if I thought maybe I had done something wrong, I would want to check my mode on my calculator. And this is true for any calculator you're working with. It needs to be in degree mode, which mine is. So I know this value to be correct. And me personally, I just like 2 decimal places for things like this. There's no indicator here as to how I should round, and I want to make sure there's at least some rounding involved. So that was negative 6.936. So we'll say negative 6.94 to represent our x component. And then we're just going to go in a very similar fashion. In fact, I'm going to hit second enter to retype in my previous problem And I'm just going to scroll over to the cosines and just turn them into sines instead. And that way I don't have to retype everything in that problem. And I see that for this version, we have negative 1.18 for our y component. So negative 1.18 for our y component. And so again, we want to think maybe we did something wrong. Who knows? Would that negative be a problem? And I say, well, 139 we said was in the second quadrant. This here was in the third quadrant. But I feel as though this is so close to 270 as to almost be pointing straight down, whereas this 139 is really non-committal as far as things go. It's not too close to 180, although it's getting there. It's actually pretty close to in between, so it's doing something kind of like this, kind of in the middle. It's not pushing up as strongly as the other vector is. So this negative 1.18 actually feels pretty okay to me. I do feel like it would stay somewhat in that negative region there. And you could verify this in other ways, but for our purposes here, this is what we expect to see. And this would be our final component form for adding up our vectors A and B. So anytime you're given two vectors, regardless of the form they give those in, so here we had magnitude and direction. We've seen it already given in component form. We've seen it where they gave us initial and terminal sides or points. Any of those we can work with. We can add those vectors together just by converting everything into components and then bringing it all back together by adding up your x components, adding up your y components. If they ask for any other information, magnitude or direction, you can get that from your component form.